after review of some concepts that we have already seen earlier in the earlier classes, courses, in the first module, we looked at some relationships that would be fundamental to thermodynamics and their interrelationships in module number 2. In this module, module 3, we will look at thermodynamic properties of pure fluids. Fluid, as may be known, is either a gas or a liquid, and let us continue the theme that we looked at in the later part of the previous module here also. First, easy to measure thermodynamic properties PVT of gases we will look at, and then we will do an extension as appropriate to liquids. Initially it will be that of gases and then to liquids, and later express other thermodynamic properties such as internal energy U, entropy S, enthalpy H, Helmholtz free energy A, and Gibbs free energy G in terms of the more easily measurable pressure, specific volume, and temperature. We all know what an ideal gas is, and let us state it here for completeness. The relationship between PV and T for the so called ideal gases must be very familiar. It is PV equals RT. Let us register this as equation 3.1 here, because we will need to refer to this in the later parts of the module, or maybe later too. R, as may be known, is the universal gas constant, the value of which in these set of units is 8.314 joule per mole per Kelvin. V is the molar volume or volume per unit mole of the gas that we have already seen, and this may or may not be known. In an ideal gas we get such a simple relationship because at the molecular level there are, we consider no interactions between the molecules or the particles, to make it general, that comprise the gas. So that is what led to the ideality of the gas, no interactions. Now take a look at this. In terms of the chemical potential mu that we defined in module 2, we can write the ideal gas, or we can define the ideal gas as mu equals a certain mu naught plus R times T, temperature, times the natural log of the total pressure P. We will call this equation 3.1a. Here mu naught is a function of temperature alone. This mu naught is a function of temperature alone, and therefore another way of looking at this equation, interpreting this equation, is that ideal gas is one whose chemical potential mu at constant temperature, which means this will be a constant, RT can be taken as a constant at constant temperature, is a linear function of the logarithm of its pressure, the natural logarithm of its pressure. It is one of the ways of interpreting the ideal gas in terms of the chemical potential. This may also be known that noble gases such as argon, krypton, xenon approximate well to ideal gases. Most gases are non-ideal, or they can also be called as real gases. So what is the formulation that we could use effectively for real gases? Also the as may be apparent, if it is a real gas, it is not going to follow the ideal gas equation, or in other words, for real gases PV is not going to be RT equal to RT, or the chemical potential mu of an ideal pure gas cannot be expressed as mu naught plus RT ln P. Therefore, we need another variable, and that variable happens to be called fugacity F, which is used for real gases. The fugacity of a gas, in fact fugacity is a little general. If we are going to define it for real gases, it should be applicable to ideal gas in the limiting case. That is always the case. Whenever you generalize, it should also take care of a special case. Therefore, the fugacity of a gas, either ideal or real, is defined as, or it can be obtained from this expression, the chemical potential mu equals mu naught plus RT ln F. Note that for a ideal gas it was mu equals mu naught plus RT ln P. Here instead of P we are using this fugacity here. This is not the complete definition. We should also add that F fugacity by total pressure P tends to 1 as the pressure tends to 0. This is the complete definition of a real gas, or of a gas, whether real or ideal. Let us call this equation 3.1b. And as mentioned earlier, under limiting conditions it should become an ideal gas, and of course it is quite evident that mu equals mu naught RT ln plus RT ln F should become mu equals mu naught plus RT ln P, and therefore fugacity must equal pressure for the ideal gas. This F by P is an interesting quantity, and let us define it as a separate quantity here and indicated by the letter phi. We will call this equation 3.1 C, and phi is actually called the fugacity coefficient. F was fugacity, phi, which is the ratio of F to P, is called fugacity coefficient. We already saw that real gases are not going to follow PV equals RT, and therefore we need more accurate mathematical representations or more accurate models of the simultaneous variation in P, V, specific volume, and temperature. In other words, we need more accurate equations of state. In fact, the interrelationships between pressure, volume, and temperature are called equations of state. PV equals RT is a very simple equation of state. We need more complicated equations of state to represent ideal gases, to represent real gases. Let us look at a few equations of state for real gas in this course. There are many which have been developed over the past century or more. So, let us look at a few of them which are quite heavily used. The first of those equations of state that we are going to look at is called the Virial equation of state. To get to know what Virial equation of state is, let us first define PV by RT. You know, PV was equal to RT for an ideal gas. Let us define PV equal by RT as a certain Z, where this, let us call this equation 3.2, and this Z is called the compressibility factor. The Z can also be expressed as a power series in P. You would have learnt about power series expansions in your mathematics classes, and if it is expressed as a power series, it is called a virial expansion. We will first look at the expansion as a power series in pressure. Z can be written as 1 plus a coefficient B2 times P plus B3 times P squared plus B4 times P cubed plus B5 times P power 4 and so on. This is the power series expansion in pressure, and this is called the virial expansion or virial equation of state for the particular component, which is represent for the particularity of the gas comes about through B2, B3 and so on, as I will explain in a little while. We will call this equation 3.3. B2, B3 and so on are called virial coefficients. B2 is called the second virial coefficient, B3 is called the third virial coefficient and so on. These virial coefficients represent the interactions between the molecules or the particles that comprise the gas, typically molecules. For example, B2 represents the interactions between particles in a gas taken 2 at a time, considered 2 at a time. B3 represents interactions between molecules taken 3 at a time and so on. Therefore, the virial coefficients can be calculated from theory, which is actually statistical mechanics, which we will not be covering as a part of this course, but statistical mechanics looks at the way of counting and way of accounting for molecular properties and so on, and molecular doings and so on, and their relationship to macroscopic properties such as internal energy, entropy and so on. So from very basic theory, we can calculate B2 and B3. Here I am not going to show you those calculations, I am just going to probably present the expressions maybe later on. And as mentioned earlier, virial expansions with unique virial coefficients for each gas can be written. Therefore, B2, B3, B4 and so on are going to be different for different gases. For low enough pressures, say until a few bar, few atmospheres, the first two terms of the virial expansion alone are good enough to give accurate enough results. As we increase the pressure, we need to add more and more terms for the accuracy. What do we mean by accuracy? How close is the calculated value to the very carefully conducted experimental value? Higher the pressure, more the number of terms, more the number of virial terms needed for accuracy. The virial expansion, as we said, is nothing but a power series expansion. It can be written in terms of molar volumes also. For example, Z can be written as 1 plus C2 by V plus C3 by V squared plus C4 by V cubed plus C5 by V power 4 and so on. This is a power series expansion in V or 1 by V, and we will call this equation 3.4. C2, C3 and so on can also be calculated from theory, similar to the calculation of B2, B3 and so on. Now, we have looked at some new information. So, let us work out an example or an exercise to understand this and apply and gather the skills of application a little better. This is example 3.1. Isopropanol or rubbing alcohol has many biological uses. It is used as a drying agent to prevent swimmer's ear. It is also used in sterile pads to store biological specimens and even in certain laboratory procedures such as the one to extract chromosomes. So, it has very many applications, and you will find that we will be using isopropanol as one of our model substances for presenting the applications in this course. We will use it quite heavily. In one of the steps that was experimented to optimize isopropanol production, it became necessary to heat pure isopropanol to 200 degrees C and increase its pressure to 10 bar. What is required here is estimate the volume of the vessel necessary to maintain the above conditions for 1 mole of isopropanol. Compare the value with that obtained by considering isopropanol vapor to be an ideal gas. So, that would quickly give you what are the kind of variations that you would expect when something is real and you use an ideal gas expression to represent it. And to do that, we will need the virial coefficients for isopropanol. These are available in the appendix of your textbook at the back. For ease, let me present it here itself. C2 is, remember C, the coefficients in the virial expansion with respect to V. So, C2 equals minus 3.9 into 10 power minus 4 meter cube per mole. C3 is minus 2.6 into 10 power minus 8 meter per 6 per mole squared. So, please go ahead and work this out. Take about 10 minutes. After about 10 minutes, to think through the problem to see what is available, what is needed, how do you make the link between what is available and what is needed. Go through all your notes, the previous slides here, and then I will start giving you some hints and then give you more time and then probably present the solution. Go ahead, 10 minutes please. Okay, let me give you some hints to work out the problem. The first hint, which was quite obvious once you thought through it, was consider a Virial expansion in V, and the real hint is take the first 3 terms. And let me also give you the second hint and leave you for another 10 minutes to work things out, and that is the solution is not a very straightforward solution, it involves an iterative solution. So, set up an iterative solution process for V or in terms of V, because the specific volume is what we are looking at, the volume of the vessel that will hold 1 mole of the substance, which is essentially the specific volume, is what we are looking for. And so, set up an iterative solution process for the same. Go ahead, please take another 10 minutes. Okay, let me present a part of the solution and give you some more time, because I am not very sure how comfortable you are with the iterative solution process. So, to get more comfortable with that, I probably need to give you more time, but first let me present the initial part of the solution. Let us begin with the first three terms on the right hand side of equation 3.4. 3.4, if you want, you can go back and check your slides. It is nothing but the Virial expansion in V, or the compressibility factor Z, expressed in terms of the powers of V, or 1 by V. Z equals 1 plus C2 by V plus C3 by V squared. Let us start with this. This will turn out to be decent enough. We are trying to find out the volume, and therefore we need to express this in terms of the volume. Therefore, for our purposes, it can be written as, Z is nothing but PV by RT. Therefore, if you multiply both sides by RT by P, we get V remains here, the remaining get cancelled out, RT by P into 1 plus C2 by V plus C3 by V squared. Let us call this equation 3.4. I will check the numbering in a little bit. It is the same, pretty much the same, with just the 3 terms taken. This is the equation, and this can be solved iteratively for V. Let me give you the algorithm to do it, because we need to do very many calculations, and once I present the algorithm, I would like you to take the remainder of this lecture, maybe another 10 minutes or 8 minutes, to work that out. Maybe you will need a little bit more time, it takes a few steps to converge. Let me present the algorithm first, or the procedure. First, guess a value for V, substitute it into the right hand side to find a value, in terms of C2, C3 and RT by P and so on. Guess a value for V, substitute it here to get a value, and compare that with the guessed value. Remember that V was something that we guessed to begin with the first time, and then we substituted the same V here to find out this value, and now compare the right hand side with the left hand side. If the calculated value, the right hand side, is close enough, the operative term here is close enough, you might be working with 10 power minus 3 and so on and so forth, but if all the values are in the range of 10 power minus 3, it is not really close enough to the guessed value, then the guessed value is the needed value. Otherwise, the calculated value is used as the guessed value for the next generation. Whatever you calculated here, you put it here and then substitute it back here to get another calculated value, and then you check how close this is to the guessed value or the value in the previous step. The process is continued till the difference between the calculated and the assumed value becomes acceptably small. Okay. Please go ahead and do this. Try doing for about 5 steps, that is a hint. So, try doing for about 5 steps, and when we begin the next class, I will give you the complete solution.